Today, in the 9th week of second lecture, in continuation, let us discuss about climate technology, particularly the technologies that are available for mitigation. So, what are the technologies in terms of some examples? We'll take 5 as far as the concepts are covered. We will talk about the solar photovoltaic technology. We'll talk about the wind technology. We'll also talk about the electric vehicles and heat pumps. We'll talk about the green hydrogen, and we'll also talk about the CCUS, that is carbon capture, utilization and storage technology. So, with these 5 we have picked for our discussion in today's class, that is 42nd class, and through this we will try to understand how these technologies are useful in terms of mitigating the climate change or climate related disasters and happenings. So, first is in terms of the solar photovoltaic technology, we understand that they convert the sunlight directly into electricity using semiconductor materials. We also know that the wind energy technology converts the kinetic energy of air currents into electricity using the wind turbines. Third is the electric vehicles and also the heat pumps. These are the two most critical technologies because they replace the combustion of fossil fuels with high efficiency electrification as far as the electric vehicles are concerned, or EV. The fourth one is the green hydrogen. It is actually the hydrogen which is produced via electrolysis powered by renewable energy, particularly solar, wind and hydro, that splits water into hydrogen and oxygen with zero carbon emission. Moving on to CCUS, this is a suite of technologies that captures carbon dioxide emissions from industrial processes and power generation to either reuse them or to store them permanently in some other locations, and mostly we use the underground locations that we call the geological storage. That is how we prevent the release back to the atmosphere. Moving on, as far as the solar photovoltaic cells are concerned, as I just mentioned, that this photovoltaic technology converts the sunlight directly into electricity. So, solar energy is converted to electricity using the semiconductor materials. So, these semiconductor materials are typically silicon, and this effect we say that photovoltaic effect. So, it is a clean renewable source because solar energy, it is available to us and it powers the devices including our home appliances and also grids via solar panels. That means we can store the renewable energies which are captured through the photovoltaic effect or by the photovoltaic cells. We can store it in the grids for our later use. It is the key advancements in terms of high efficiency, bifacial and perovskite cells. So, the advancement in terms of this actually has helped the solar photovoltaic technology to grow faster and to grow ahead. So, coming to the key components and the types, the photovoltaic cells, they are the fundamental unit. The PV cells are the fundamental unit that converts the photons or light into electrons, that is in terms of electricity. The panel or module, we have multiple cells connected to boost the power output. There are arrays. So, arrays are a linked connection, or you say the collection of modules for higher capacity. And then we have inverters in the photovoltaic system. So, the inverters, they convert direct current, that means DC, produced by the panels into AC because we need to minimize the loss in terms of the current. for grid for appliances. So this conversion DC to AC we do for grid or any other appliances for use by any other appliances. Then coming to the system configuration, we can have two types. We can have grid connected systems, that is a standalone system. We can also have this is mounted based on fixed, either a stationary platform or tracking that follows the sun system. So with tracking being more efficient, because you follow, or the solar panels, they follow the direction of the sun, so as to track or to capture maximum of the incoming solar radiation to fall on the panels. So advanced and future technologies, as far as this has been mentioned in terms of bifacial models, in terms of PSCs, that means peroxide solar cells. These are emerging materials aiming for high energy efficiency, and also the tandem cells that talks about that are the stacking different materials to capture more of the light spectrum. And the bifacial models, they collect the sunlight on both sides with the TOP-CON technology, the TOP-CON technology, reducing electron recombination for higher efficiency. Moving on to the solar photovoltaic in detail, have a look at the solar photovoltaic system and how it looks like. This on the right hand side I have put a graphics or depiction of that. So in order to produce a photovoltaic cell's electric field, the manufacturers create a junction by joining the two distinct type of semiconductors, that is P and N, which generates the electric field within the photovoltaic cell. So now adding an element with an extra electron or an electron shortage is most common technique for producing the P-type or N-type of silicon material. The ability of a photon to excite an electron depends on the band gap energy of the semiconductor material. So when a photon transfers enough energy, an electron is excited from the valence cell or valence bond to the conduction band. Thereby it creates an electron hole pair. So now look at the type in terms of the built-in electric field at the P-N junction. Look at the P-N junction there. So the built-in electric field at this junction, P-N junction, then plays a crucial role in terms of separating these charge carriers. So thereby it directs the free electron towards the N-type region and holes towards the P-type region, thereby generating an electric potential difference. This movement, you can see now, this movement of electrons result in the formation of an electrical current when the circuit is closed. However, but some charge carriers may recombine before contributing to electricity generation, thereby reducing the efficiency. So as I mentioned, we have two types in terms of standalone or grid tied. On the upper side of the depiction, you can see it is the standalone. That means you have a battery energy storage system. And the second one is the grid tied system. That means it is tied to some kind of electric grid in terms of the storage of the electricity. So coming to the standalone and grid tied type of solar photovoltaic systems, the features, advantages and limitations. As far as the features are concerned, for the standalone types, it operates independently without the grid connection. It requires battery storage for energy use during night time or low sunlight also. So it is suitable thereby for remote locations, emergency power, telecom sites, water pumps and street lighting. But look at the features as far as the grid tied solar photovoltaic systems are concerned. It is connected to the utility grid for energy exchange. So no need for in contrast to standalone, in this kind of grid tied system, there is no need for battery storage as excess energy is fed into the grid. It is usually common in residential, commercial and industrial settings with grid access. Now, what are the advantages? As far as the advantages of this standalone photovoltaic systems is concerned, it provides electricity in areas without grid access. It ensures power availability during grid outages, and then it can also integrate with other renewable sources like wind or biodiesel generators for reliability. Coming to the grid-tied solar photovoltaic systems, the advantages are it reduces the electricity bills through net metering, that means selling the excess energy to the grid. No battery cost, thereby it reduces the installation and maintenance expenditure. But it has higher efficiency as power is used immediately or is credited to the grid. So this has a huge, these are the advantages as far as the grid-tied PV systems are concerned. Now let us move on to the limitations. So one is the limitations of other and vice versa. In that way, let us see for the standalone PV system, the high initial cost due to battery storage, battery maintenance and replacement costs, limited power supply when solar generation is low and batteries are depleted. In terms of grid tied, you can see no power supply during grid outages unless a backup battery or a generator is installed. It requires utility approvals and compliance with grid regulations. Potential interconnection fees and dependency on the grid stability is needed. Now look at the depiction in terms of DC load, direct current, and you have the AC load, you have the DC-AC inverter, you have a controller as far as the DC load is concerned, and also as far as the battery energy storage. Similarly, for the grid tied solar PV, you see you don't have there is a net meter with respect to connected to electricity grid and AC load, and you have a controller switch that converts or inverts between DC and AC. So that is the difference between these two. Now move on to the next energy, that is wind energy. In terms of wind energy, this technology converts the kinetic energy of air currents into electricity using the wind turbines, primarily featuring three-bladed horizontal axis design, or we say, if it is horizontal axis design, we say that HAWT. So horizontal axis wind turbine. Modern turbines, both onshore and offshore, use aerodynamic lift to spin a rotor, thereby driving a generator to produce power for the grid. So there are various advancements. They include larger, more efficient blades and smart and also AI-driven control technologies for optimization. What are the key components as far as the mechanism is concerned? We have a rotor, the nacelle, the tower, the types, particularly the horizontal and the vertical axis wind turbines, and we also have a control system. So the key aspects of modern wind technology are onshore versus offshore, and efficiency and growth, and the future focus. So let us see a comparison between the horizontal and the vertical axis wind turbine. On the upper right hand side, you can see the two depictions. On the left hand side you have for horizontal, and the right hand side you have for the vertical. And look at the comparison with 10 points. First, for horizontal, the rotating axis of the wind turbines remain horizontal or parallel with the ground, whereas in terms of the vertical, it remains vertical or perpendicular to the ground. In terms of the second point, it is able to produce more electricity from a given amount of wind, whereas in terms of vertical, it produces 50% more electricity on an annual basis versus the conventional turbines with the same swept area. So the vertical one produces 50% more. In terms of the horizontal, it is suitable for big wind applications, but the vertical it is suitable for small wind projects and residential applications as well. As far as the horizontal is concerned, it is comparatively heavier and not suitable for turbulent winds. Whereas in terms of the vertical, it is lighter and produce well in tumultuous and tumultuous wind condition, that means relatively less, and disturbing wind conditions also. Coming to the horizontal, they only are powered with the winds of the specific directions, whereas the vertical axis turbines are powered by wind coming from all 360 degrees, and even turbines are powered when the wind blows from top to bottom. Similarly, the horizontal is not suitable to generate electricity from the wind speed below 6 meters per second, and generally cut out speed is 25 meters per second. Whereas in case of the vertical, it generates the electricity in winds as low as 2 meters per second, and also continues to generate power in wind speeds up to 65 meters per second based on the model. In case of the horizontal, they cannot withstand extreme weather conditions due to frost, freezing rain, or heavy snow plus the heavy wind in excess of 50 meters per second. So if more than 50 meters per second, that means it is difficult for the horizontal axis wind turbines. Whereas in case of the vertical, it withstands the extreme weather such as frost, ice, sand, salt, humidity, and very high wind conditions in excess of 60 meters per second. Coming to the 8th point, for horizontal, birds are injured or killed by propellers since they are not solid objects, so the birds fly into the blades. Whereas in case of the vertical, it doesn't harm the wildlife such as birds, because it can detect a solid object and can be seen on a aircraft or radar. So similarly, for the horizontal, it is most are self-starting. In case of vertical, low starting torque and may require energy to start the turning. And the horizontal axis wind turbines, as a WT, are difficult to transport and install, whereas this is relatively lower construction and transportation cost is there for the vertical axis wind turbines. So look at the depictions. You can see the wind energy flux swept area for HAWT, that means horizontal, and for the vertical axis wind turbines. So so we can see the growth in size of the commercial horizontal axis wind turbines. You can see on the upper right hand. So it has moved up to 15 meter to 300 meter in terms of the size as far as the commercial appliances are concerned. So in terms of the features, the development trend, potential challenge, and solutions as far as wind energy technology is concerned. So wind turbines, last 3-4 decades, the HAWT dominated the wind turbine world. R&D continues on VAWT in full phase, as it is individually more effective than HAWT. So the turbine height is increasing day by day. You can see from the depiction. The turbine capacity, it has also gone from 20 to 500 kilowatt, but now it has gone to 2 to 5 megawatt. So turbine blades have also moved in terms of size from 1 to 3. Power generation, by using the same space, VAWT is able to produce 10 times more wind energy than HAWT. Power density for HAWT is 10 to 12 times more than the HAWT, and land requirement is relatively less for VAWT in comparison to the horizontal axis wind turbine. So energy storage, previously the energy storage system was not so much necessary, but Now it is mandatory for wind farms or wind energy generation has increased significantly. That means the fuel cells and batteries are the two most impactive energy storage devices in RE system. So in both the cases, the fuel cells and the batteries, they help or they support as far as the energy storage system is concerned. Space and efficiency, we have already we know that the space is much more demanding concern when it is considered as per the HAWT than that of the vertical axis wind turbine. Now, let's move on to the third one in terms of the electric vehicles or the heat pumps. The electric vehicles and heat pumps are two most critical technologies for global climate mitigation because they replace the combustion fossil fuels with high efficiency electrification. Together, they address the two largest sources of greenhouse gases emission, that is transportation and the building heat. The green hydrogen is rapidly scaling through electrolysis cost, need reduction for broader adoption. It is considered a crucial component for the India's energy independence and in terms of achieving the long-term climate goals. Here in terms of depiction, you can see in a vehicle that the different places, transmission, charger, AC-DC, DC-DC converter, you have the charge point, battery, power electronics controller, traction battery pack therein, power inverter and the electric traction motor. So that is how it is fitted in terms of the electric vehicles. Coming to the climate mitigation potential, it has a lot of decarbonization potential as we know. In a scenario aligned with 1.5 degree global warming target, the cumulative in terms of avoided emission by 2050 are estimated at 12 gigatons of carbon dioxide for the EVs. That means due to the battery displacement of fuel, and 4 gigatons for the heat pumps. So 12 and 4 particularly for EVs and the HPs. So efficiency advantage, EVs they convert 90% of the electrical energy into motion. Heat pumps, instead of creating heat, they move it, delivering 3 to 5 times more heat energy than the electricity they consume. So the efficiency is to the tune of 300 to 500% in terms of the efficiency. Now, the synergy. In terms of synergy, we have the grid flexibility, share technology, and the sector coupling as far as the synergy between the EVs and the heat pumps are concerned. Moving on to the green hydrogen. The green hydrogen is the hydrogen produced by electrolysis powered by renewable energy in terms of solar, wind, hydro, and similar ways. And thereby it splits the water into hydrogen and oxygen with zero carbon emission. It is essential for decarbonizing the heavy industries like shipping, steel, and chemical manufacturing. India's national green hydrogen mission aims to produce 5 million metric tons of energy from hydrogen in terms of per annum by end of this decade. So the key aspects and in terms of green hydrogen is the production process, particularly it uses the electrolyzers powered by renewable energy sources, ensuring greenhouse gas emissions. That ensuring no greenhouse or minimal greenhouse gas emission, it is almost nil. The significance is it serves as a sustainable alternative to traditional fuels with applications in transportation, power generation, and chemical industries. In terms of Indian context, the mission goal, India has initiated the NGH, that means the National Green Hydrogen Mission, with a budget of 19,744 crores, intending to make India a global hub for production of exports. Targets achieve 5 MMT annual production capacity by 2023, along with over 125 gigawatts of associated renewable energy capacity. The cost goals is this: target to reduce the production cost to 1.5 USD per kg by 2030. In terms of infrastructures, initiatives like the Green Hydrogen Hub at a at Tuticorin port are being developed. So you can see in terms of the depiction on the upper right corner, the gray hydrogen, the blue hydrogen, and the green hydrogen. Gray hydrogen it emits, blue hydrogen it also, whereas we are talking here in terms of the green hydrogen. So advantages: it is highly efficient and sustainable, offering a solution where direct electrification is not possible. Now moving on to the CCUS, carbon capture, utilization and storage technology. Friends, let us understand what it is in terms of carbon capture, utilization and storage. As we know, the carbon dioxide, or in general the carbon, has 4 residences. The largest is the lithosphere, or the underground, right? And that contains about 99.96% of the total carbon what is available. So 99.96% of the carbon is stored in the geological sphere or in the lithosphere. Second largest reservoir is ocean. It stores about 38,000 petagrams of carbon, and remaining about 2,000 petagrams of carbon, soil stores about 1,500 petagrams, whereas some about 500 plus, about 560 or so petagrams of carbon is stored in the plant materials. So what is happening? Through various activities, the carbon is escaping from these reservoirs and getting into the atmosphere. So now, using various technologies, particularly the CCU technology, talks about withdrawing the carbon or carbon dioxide from the industrial sources, or you say the point sources, where in terms of industrial sources or the power generation sources, where the emission is in a substantial amount. So that means CCUS is a suite of technologies that captures the carbon dioxide emissions from industrial processes and power generation to either reuse them or store them permanently underground, thereby to prevent the atmospheric release. So you can see from here we have 6 different ways in terms of storing it at a geological storage, and also offshore in terms of the oceanic storage. Now you can see the first one is number 1, the carbon dioxide which is taken or which is captured from the industrial sources can be stored in terms of depleted oil and in the places where the oil and gas reservoirs have been depleted. It can also be used to to enhance oil recovery. That means the carbon dioxide can be used as a pushing material or a pushing source, so that the oil will come up on this side. You force the CO2 compressed gas and it pushes the oil to come up. So that way you can see the number 2, it is shown there. And the number 3, in terms of deep unused saline water or water saturated reservoir rocks. So at those places we can also store it where it is unused saline water saturated places. The 4th one is in terms of deep unminable coal seams, and also the 5th one is the use of carbon dioxide in enhanced coal bed methane recovery. And the 6th is other suggested options in terms of the basalt, oil cells and cavities. So these are the places where the carbon which is captured from various industrial sources or the dominant carbon emission sources can be stored. So this technology is called the carbon capture, utilization and storage technology. And also there is another way we can take this carbon or carbon dioxide which is captured from industrial sources, carry it and store it in the oceanic sources or in the ocean environment. So that is called as the ocean storage. So geological storage and oceanic storage are 2 options as far as the captured carbon is concerned. from the atmosphere or from various industrial sources. Now, we have used these references for preparing the slides, and the materials have been picked from there. And coming to the conclusion, yes, we discussed about solar photovoltaic technology. We discussed about wind energy technology. We also discussed about the electric vehicles and the heat pumps, the green hydrogen, which is produced by electrolysis, and also we talked about the carbon capture and utilization technology. So these 5 technologies we discuss as an example in terms of mitigating as far as the climate related technologies are concerned. Thank you very much for your interest.